Want to learn something about fluid mechanics? My favorite thing is Bernoulli's equation. It relates the pressure, velocity, and height of a fluid at one point of a system to the pressure, velocity, and height of a fluid at another point in a system. This is the equation right here. This P1 right here is the pressure at point 1. This rho underneath is the density of the fluid. V1 is the velocity of the fluid. G is the acceleration due to gravity. And Z1 is the height at point 1. This height is measured with respect to a datum, which is an arbitrary zero assigned in the system. The pressure, velocity, and height at point 2 are on the other side of the equation. There are several assumptions made so that this equation can accurately depict the system. These assumptions are that the fluid is incompressible, which means that the density does not change due to an increase in pressure. The system is frictionless, meaning that there are no losses due to friction between the fluid and the system. The system is along a streamline, meaning that point 1 and point 2 both lie along the path of the fluid, and the system is also at steady state, meaning there is no change in the system with respect to time. Now we have a little experiment to show you guys. Our experiment is watching fluid flow through exit nozzles of different diameters. Here's our system. Point 1 in our system is at the surface of the fluid in the funnel. Point 2 in our system is outside the nozzle at the end of our tube. Here are the simplifications and assumptions to Bernoulli's equation which relate it to our system. First of all, both pressures are zero because the fluid at the beginning of the system, which is the top of the funnel, and at the bottom of the system, the nozzle, are both at atmospheric pressure. V1 we are assuming to be zero because at the top of the funnel is a large reservoir of fluid, so the surface is not moving. Z2 is zero because our datum is at the level of the bottom of the tube. So this equation simplifies to GZ1 is equal to V2 squared over 2. Here again are the simplifications we made to relate Bernoulli's equation to our system. Even though our system is not technically at steady state because the height of the fluid is changing over time, we are still using Bernoulli's to conceptually explain how the velocity changes and how the height changes and how they are related.
After we release the valve, the height of the liquid in the funnel will begin to decrease. This represents Z1 in the simplified form of our equation. As you can see from the equation, as Z1 decreases, there must be a decrease in V2 as well. V2 represents the velocity of the liquid after it exits the nozzle. As the velocity of the liquid exiting the nozzle decreases, the radius of curvature of the path of the fluid will decrease as well, as you can see in our demonstration.
Let's move on to the next concept, conservation of mass. Conservation of mass tells us that the mass flow rate going into the system must be equal to the mass flow rate exiting the system. Since we are assuming the system is an incompressible fluid, density is constant, and volumetric flow rate up to the first point must be equal to the volumetric flow rate at the second point. So our equation simplifies further to velocity at point 1 times diameter at point 1 squared equals the velocity at point 2 times the diameter at point 2 squared. This equation tells us that as the diameter decreases, the velocity must increase to counteract that change.
As the conservation of mass states, assuming an incompressible fluid and equal flow rates, the velocity multiplied by the area at one point in the tube will be equal to the velocity multiplied by the area at another point in the tube. Therefore, when the cross-sectional area at the nozzle is greatly decreased by adding a funnel, the velocity of the fluid must increase to counteract that change. The velocity of the fluid exiting the nozzle is therefore greater than the velocity of the fluid flowing through the tube. This is evident in the following video. By looking at the top level of fluid in the tube, you can tell that the distance traveled per unit time of the fluid in the tube is much slower than the high-velocity fluid exiting the nozzle. This shows the effect of the conservation of mass.